Hello, everyone. Ioannis here. So as Nachman said, I'm a solution engineer with SimScale, working here for the past 2 years now. And I'm here today. I have the pleasure today to have with me Paddy, who is joining us from Handbike Wheels. And together we are going to present some success stories that SimScale and Hand were able to do together. So maybe a few words about yourself, Paddy, before we start.
Yeah, hi there, everyone. I'm Paddy. I'm the development engineer at Hunt Bike Wheels, predominantly focused on the road side, but some mountain bike as well. And I've been at Hunt for coming up on 4 years now.
Perfect. Thanks a lot, Paddy. Paddy will take over again later, where he will present more specifically on what Hunt Bike Wheels are doing, and also talk a bit about the simulation results they got and the performance, the improvements they managed to get. But for now, let's start the slides. First with the agenda. So today, this is what to expect today. So we'll do a quick SimScale introduction for those of you that don't know us. And then we'll pass over to the actual case study spotlight by starting with introduction to Handbike Wheels and what they're doing. And also we'll move on with a live demonstration of the SimScale platform by specifically looking at one of Handbike Wheel projects. And last but not least, we will follow up with a Q&A session where you can literally just ask us anything, and we'll try to address all of your questions within the time. So roughly, we plan to spend around 45 minutes for this webinar. So yeah, sit back and just enjoy. All right, so a few things about SimScale first, and I promise I'm gonna go quick, and then I'll get you right into the interesting stuff. But yeah, SimScale is a simulation company. We built the SimScale platform, and we're a cloud-native solution. Currently, we have more than 500,000 users all over the world, and customers in more than 50 countries, right? What's really cool is that we actually started at Munich. So our headquarters are in Munich, Germany, but we very quickly expanded to the US, right, with 2 offices. And also we're looking at an expansion to other regions of the world. So SimScale is basically a simulation platform, right? We can basically do CFD, FEA, and electromagnetic simulations right from your desktop. So basically, you just don't need any hardware, and you just can do it from anywhere you are, right? Right, either the office or home, or if you're traveling. Currently, with SimScale, we are more than 130 people, and we keep growing. And we're basically located all over the world to also support the customers we have all over the world. So if we take a look at what is the engineering trend right now and where is the innovation going to, right? We have this, I mean, of course, we have many more different verticals, but let's say we have this, let's say, main verticals that we see the most of the stuff being happening. So we got electrification, energy transition to clean means of energy, right? Automation, space applications, and also net zero cities, right? So SimScale is basically supporting with simulation capabilities and tools all of these major verticals, but of course all of the engineering verticals that are out there. And as a proof of that, you can basically see the huge portfolio of our customers listed over here, and those are just some of our customers, right? Feel free to visit our website and get an idea of what exactly we're doing, who are our customers, and check out case studies and success stories. One of the success stories we're exploring today with Handbike Wheels. So now I talked about simulation, right? I talked about all the physics, but let me give you also a brief intro to the platform itself. So here we see a screenshot of how the graphical user interface of SimScale looks like. Of course, we'll get into a live demo afterwards, so you'll basically get a better idea. But if I want to highlight the 5 main differentiators of SimScale, and what is actually tearing us apart from the competition, is first of all, we're cloud native. So nowadays you might hear a lot of vendors coming up and saying we are cloud-based, we offer cloud-based solution. We believe that's not correct. So the correct term here is cloud native, meaning that SimScale was entirely built on the cloud from scratch, right? We started at the cloud and we keep going on the cloud. So it's an entirely cloud native solution, nothing to do with local hardware or infrastructure, right? Everything is on the cloud. We have, in our platform, we support a wide range of physics. So we support, as you can see over here, both CFD, fluid flow analysis, also thermal analysis, but as well as also structural analysis. And recently, we have also added electromagnetic simulation. Now, since we are in the cloud and we're basically accessible from anywhere, we have taken collaboration to the next level. Imagine it like a Google Docs type of collaboration, right? Where anyone can log in into a project and collaborate with each other, right? One can create a simulation, the other engineer can basically just maybe evaluate the results. Another engineer may copy my project and do something else, right? So this whole collaboration capabilities are made available through SimScale, right? That's basically really hard to find in any other simulation tool. And since we are in the cloud and we allow multiple simulations to be run in parallel, so you can run many simulations in parallel. You can anytime use this large amount of data to create your AI models in the future, right? So recently we've been into the AI market, so we're launching a new AI solution. I believe we also had a past webinar about it. So all the data you have in SimScale, you can then use this to train your own AI models and basically just take your simulation and design capabilities to the next level. And this is basically unlocked by the power of the cloud in SimScale, where, as I told you, you can basically just run any number of simulations in parallel. And instead of having to wait minutes and maybe hours, if you were about to do that locally on your local workstation, for example, you can basically just skip this obstacle and just do everything in parallel. So like in this case, for example, I run 4 simulations at the same time. And that way, in an hour, for example, I got all the results. Now, let's take a look at this example, just to give you an idea of what does SimScale multiphysics mean. So this is an electric motor we see over here. And we use this example because it's a very good example to show you what type of physics we can do, right? So first of all, we can do standard fluid flow analysis where, for example, you have a cooling channel and you want to see the shape of it, you want to study the pressure drop, right? So that's standard CFD analysis. Of course, you can also include thermal analysis on top, so you can do conjugate heat transfer, convective heat transfer analysis, right, in the motor and see how well this cooling channel actually manages to cool down the motor. And then you can also go to the other side and start doing structural analysis using our FEA solvers. For example, here we do a frequency analysis. You can also do static structural. We'll see all the different types later. And finally, a couple of months ago, we've also included electromagnetic capability. So in the actual motor, you can basically simulate the magnetic fields, and we have capabilities that are quite quickly expanding also in this field. And before I give it to Patty, let me just give you an example. Right? So how an engineering team can utilize SimScale. First of all, why you need to simulate, right? So simulation is becoming more and more important nowadays, where you can see, I mean, I'm working in the field, right? I see that more and more people willing to simulate, not only the experts right now, but also, let's say, designers or maybe architects, right? So people that have not been trained in the university for doing simulations have now access to simulation because we are moving in a fast-growing world, right? So we need to allow more capabilities to more people faster, right? And this is where SimScale comes to help, right? So with SimScale, you can have access to the platform, right? It's a very easy to use graphical user interface. And you can start by doing quick conceptual designs and do a design space exploration, essentially, right? So you can upload any model from your CAD, start doing some quick simulations, and eventually take it to the next level and start talking about optimization, right? So, for example, you have one bracket, you want to see, explore alternative designs, you create 5, 10, 20 different brackets, you simulate them really quickly with SimScale, you see let's say, what 3 are the best ones, and then you can basically proceed to physical testing, being sure that you've picked the best designs, right? So by bringing the simulation earlier in the design cycle, we allow more people to take control and basically just create the best products possible. We'll see more of that during the live demo, but now let me give the ball to Paddy, where he will give us an intro to handbike wheels and what they're basically doing. So Paddy.
Yeah, hi there again. Thank you for that, Ernest. Hunt bike wheels, predominantly, we make high performance bicycle wheels. We were founded by two brothers in 2015 in the south of England. And then, we've now grown to a slightly larger company where we've got an office both in South England and in Boulder. And you can see here on the photo to the right, we were represented at the Tour de France Femmes this year. And so that was a really big moment for us as a company to be represented on that higher stage. If we take you back right to the start, back to the first wheel that we produced back in 2015. Our guiding principles. Our guiding principles. So we are always focused around the rider. So everyone at Hunt is a bike rider, and so that's our big central focus, that we want to produce products that make bike riding more enjoyable, faster. And so we do that by always pushing ourselves to be leaner, more efficient, and just staying focused on providing the best product for the end user. The first wheel that we produced was the 4-season disc. And so this was something tying together off-the-shelf components that we picked out very carefully. And in 2015, Josh provided the ultimate proof of concept by winning the TCR on one of the first sets of these wheels ever made, where he rode from Belgium to Istanbul in just under 9 days on a set of them. So that was a really good validation for our products in the market, but we felt that we could do better. And so with the 48 Limitless, it's the first fully engineered wheel that we ever made. And so that was one of the very first wheel sets properly designed around disc brake specific rims, where we went much wider than you'd previously seen on the market, to 34.2 mil external width, where the normal on the market at that time was around 30 mil. So a really big step forward in aerodynamic efficiency. And this was achieved mainly through physical testing in the wind tunnel. And so, again, the next step for us has been to work with companies like SimScale, which has allowed.
Patrick, it seems that we lost your sound.
Quite good efficiencies in terms of weight and reducing the aerodynamic drag of the products, and also increasing the structural strength of some of our MTB product. So that's just a quick overview, and happy to answer any more questions about the company at the end.
Thanks a lot, Paddy. So very nice intro to what Handbike is doing and the story behind it. So of course we'll have Paddy with us later on.
You're going to run us through the case studies quickly, aren't you? With a bit of the way you need me.
Exactly. So let's now move to the case studies and see how exactly Handbike wheels are basically doing what they're doing. The main focus of the webinar is basically structural analysis, but we also saved the CFD case for you to discuss in the end. But let's now focus on the main point, let's say here, which is so the case study one is how to design stronger wheels for race and mountain biking, right? So as you know, the wheels are made from aluminum or even composites material, carbon, right? In this case, we're studying the aluminum profiles that Handbike wheels is using. And basically the goal, as Paddy said, is to create wider wheels that are able to withstand the same amount of impact like the predecessors, right? And also allow more grip in the end. Of course, it's very important every time you change the shape of the wheel to understand the survivability of its design, but you cannot know that a priori, right? You need to eventually conduct some physical testing, right? Do some drop tests, like impact tests, right? To understand how these wheels are behaving. But before you reach this stage, it's very efficient to run simulations, right? FEA simulation, in this case, structural analysis, and understand which designs are the best. Of course, when you pick up 2, 3, 5 different designs that perform better, you can then move on to the actual physical testing. But you have already saved a lot of time by rejecting or approving designs at the concept level already, right? Not having to actually manufacture them and spend money and time on those. So how it's actually working right now is for wheels, like for race wheels specifically, they have to fulfill the UCI test requirements. So what the UCI test requirements say is that the wheels without the tire, right, just the rim, right, have to withstand a 40 joule impact test with a flat anvil, right? But that's very easy to pass, and that's why hand bike wheels are doing slightly different testing. So they instead of a flat anvil, and please, Paddy, anytime you feel I'm saying something wrong, just correct me. I'm sure you know better than me. But every time a new wheel is going to be, released for production, right? They have to pass certain tests. So they do this sharp anvil test with the tire on to simulate the actual real life conditions, right? And basically they put it under an angle, as we'll see, to be more realistic, because typically when you ride over an obstacle, only the side of the wheel is it's the worst case scenario, right? It's being loaded and might fail, right? So how we did it in SimScale is, of course, we try to replicate this impact test, but we do it slightly different to facilitate simulation, of course. So we just position the anvil a few millimeters before impact, and we assign an initial velocity on it, similar to the drop height. You are dropping the anvil from, let's say if it's 1 meter, you calculate the speed of the anvil after 1 meter of free fall, and you assign to it. And we just model a small portion of the wheel. We don't need to bring all the wheel in, just a 45-degree portion. And we, of course, neglect the tire, because that makes it first easier for the simulation to run faster, right? And also, it's hard to model the rubber type of materials that are in the tire, right? So we just restrict it to the rim only. The material we are using is very similar to what the hand bike wheels are using for the real products, right? It's aluminum 6069, and we are modeling the elastoplastic behavior. What we want to see in the end is basically the final shape after impact, and basically identify any high stress regions, and basically regions that experience very plastic, let's say, high plastic deformation, so that deform permanently. So that's an indication to tell whether a wheel is better than the other. Apparently, the one that deforms the less is better than the other. But of course, the physical testing is the one that should tell in the end, right? Now we saved another case study for you to discuss towards the end. That's a CFD study. So hand bike also testing their wheels along with the bike frame in the wind tunnel. So they want to not only create like a strong wheel, but they also want to create a high performance wheel in terms of aerodynamics. So as the same concept, right, as in FEA, use CFD to understand which profile is more efficient aerodynamically, and then they choose these profiles to create the 3D prototypes and test them in the wind tunnel as well. So as you can understand, wind tunnel and then also physical testing in the impact testing, the real impact testing, right, is always necessary before you move to the market, right? But simulation and SimScale helps here in being able to tell which products might be better than the others, all right? Okay, having said that, let me just exit the slides and try to go to the there you go. You can see the SimScale platform. So all I did is I just opened a new tab in my Google browser, and I just went to simscale.com, and all I have to do is log in with my credentials into my profile, right? So here you can see I'm into the SimScale dashboard, where I can see all of my different projects. I've logged in with my credentials, right? And I have different projects, CFD, FEA related. That's really cool. And for this case, for today, I just created this project called SimScale Hunt by Wheels live webinar, where we are hosting all of the different simulations. All right. So right now we are into the Warbins, as we call it, right? So I have opened the project where I have all the different geometries and everything. And as in every simulation tool, the same in SimScale, everything starts with a geometry, right? So all I do is I need to upload a model, and how to do it is just click the plus button and drag and drop my geometry. So if you take a quick look, we support all of the major CAD formats. The main CAD kernel we're working is Parasolid, but we support SolidWorks, Inventor, CATIA, Rhino. So whichever tool you're using for your designs, it's really cool, and it can work with SimScale without issues. So you just drag and drop it here. And in this case, I have uploaded 3 designs, 3 wheel designs as we discussed. So the first design, so 45-degree section of the wheel and the anvil on top, and then a second design and a third design. So the differences are that designs are a bit wider or a bit shorter, so we are starting different design variations over here. Okay, you may question why you see just half of it. It's because I'm going to model only half of the model, right, just to save computational resources. So here I'll be using a symmetry boundary condition, because essentially what's happening is it's perfectly symmetric. What you can also see here is that the anvil and the wheel is placed with an angle, right? So we are interested in hitting only one side of the rim, just to see the worst case scenario, right? The worst effect that we can achieve on this aluminum wheel. So let's take a look how easy it is to set it up now. By the way, you can see that I have already set up a couple of simulations here. We can explore the results later. But let's now take the first design and try to set it up from scratch, so that in a few minutes you'll see how easy to set it up. So I click the Create Simulation button, and you can see all the different options one has with SimScale, both CFD, but also FEA and electromagnetics. But for today, I'm going to do an impact test, so I'm going to use a dynamic analysis, right? So I'll pick this up, and I'll create a new simulation. So a new branch is generated in the simulation tree over here, and I will just name it live webinar demo for today. Right? Perfect. Now you might see we have different options over here. For those of you that are familiar with other simulation tools, you already see that this window here in this workflow is already very clean compared to other tools, right? So the process is pretty straightforward. We follow a top to bottom philosophy, right? And we try to guide the user in a way that it's very easy for him to understand how to simulate. So let's take a look and start from top to bottom. Geometry is already selected. That's good. The first thing I want to do is create a conduct, right? So the tool will automatically identify conducts. So let's see. It will automatically find any conducting surfaces. So we can see that the conduct here is already identified, right? Between the anvil and the wheel, right? I want to make this a bit bigger, right? So I would like to potentially include a bit more faces. So the first thing I want to do is include more faces, and I have used here some smart naming selections to help me do that. So I'm doing selecting the NS conduct anvil. That's already automatically assigned to the anvil surfaces, and on the other side of the conduct, I'm selecting the wheel faces to basically just highlight the region of the wheel that will be impacted. All right. Furthermore, that's a bonded conduct, but I don't want to do a bonded conduct in this case. I want to do a physical conduct. So I want to convert this to a physical conduct with a click of a button. So this basically means that now the conduct is no longer glued together, but it's allowed to slide, separate, etc. So be more like an actual impact, right? Where the body is hit and then separate. That's cool. The next thing I want to do is create, that's a drop test. So I want to create the gravity direction. So in the model, I want to say, okay, what's the gravity magnitude? 9.81 meters per second squared. And what's the direction? The direction apparently is negative z-axis. So let me quickly do this. And the next thing is create the material. So for the anvil, I'll browse for steel in the pre-populated material library we offer. But of course, I can create custom materials if I want, right? I can create my own materials, that's perfectly fine, and store them permanently in the platform. But in this case, I'll just pick up steel for the anvil. And then I will pick aluminum for the wheel. Let me select it through here. Perfect. But I just don't want to use a linear elastic aluminum. I want to use an elastoplastic because in reality, aluminum is an elastoplastic material. So after a certain point of stresses, it plastically deforms. And that's exactly what I want to see in this case. So when you're modeling elastoplastic, you can do either bilinear or multilinear. So you can import the full stress strain data of the actual material. In this case, I'll just use a bilinear material model. And I'll just go with we have two options here, either the strain hardening, where you get an angle after the yield stress, the stress is still increasing but until it fails, or you have the perfect plasticity where it's a flat line. The strain hardening is more accurate, so I'll just use strain hardening in this case. And I have found some quick data online for the aluminum T6069 that Handbike is using. And I will just quickly put the values here. 345 megapascal. And the ultimate stress is around 396 megapascal, while the ultimate strain is around 20%. So now I can save that successfully, and that's how I can specify an elastoplastic material. The next thing I want to do is create some boundary conditions. So the first thing is I want to create a fixed support and fix the anvil on one side over here, right? And then I want to create a symmetry boundary condition. And put it in the symmetry and the symmetry faces of both the anvil and the wheel, like that. So this basically ensures that we're modeling only half the model. Okay. Final thing is I want to assign some initial condition to the anvil itself. So basically, I go here. As I told you, right, we don't simulate the full free fall of the anvil from over here right to the bottom. We just assume that the anvil has reached the point right before contact and impact, and I can assign an initial velocity. And by assuming that this anvil is dropping from around 70 centimeters, the calculated velocity is around 3.7 meters per second. So I will just go ahead and do a minus 3.7 meters per second towards the negative z-axis. Another quick thing I want to do is I want to create a fixed value and assign it to the sides of the anvil, because as you saw in the PowerPoint, this anvil is basically constrained, so it can only move in the z-axis, right? So I'll basically do exactly that. I'll only allow motion in the z-axis from these two planes, so that I don't see my anvil just rotating and just flying around, because in reality it's basically restricted. And that's pretty much it. I can quickly check my settings. Maybe I want to use a bit, highest penetration here at the contact. You can read all the help. So every time you change something in SimScale, you can check all the definitions and the theory. And you can also simply just Google whatever you're not sure about and ask and see the documentation. But not only that, you can also use the live chat support, where you can just click the button here. And if you're a customer, you can basically just get live support, especially within the European and the US time zones, where we literally just try to respond within a few minutes. Okay, now I'm good to go. I can start my simulation. And this will basically start a new run in the cloud. But before that, let me explain a bit over what I see over here. So here I see an indication of, look, we are about to start a new simulation, and roughly how much time it will take. So in this case, I see that this is only going to take a few minutes, right? So that's something that I should see and say, okay, it's a demanding simulation. Why it takes so little time, right? And this reminds me already that I forgot to do something. So if I cancel the simulation, I can go back in the control, and I forgot to specify the actual simulation interval, right? So in this case, roughly speaking, I know that from my impact test, right, that the impact test is roughly taking 40 milliseconds, and that's the total duration of the time. And then, of course, I want to specify a time step, so how fine I need to save the results at, and how fine I want to be in the computation. So in this case, I can either do a 1 millisecond time step, I can go lower, higher. Always I have to basically do a quick time step independent study to see how much the time step is affecting the results. So let's go with the standard over here and just go ahead and start the simulation. So now I have a new simulation running in the cloud, and that's really cool because I can wait until the results are over. But what I can also do is I can go here and now change to another design. So now I pick a new design, wheel design 2. This is saved, right? I don't want to change anything in the contacts. I get a report that everything was mapped correctly because I used the name selections over here. So I'm really good to, all my boundary conditions and materials are preserved. I'm really good to start a new simulation. And that I'm going to name it design 2. And then a new simulation is started. The same I can do with design 3, etc., and as many designs as I have. And I can have as many simulations in parallel as I like. Say I want to change the material, study a different material, I can do the changes and run a new simulation. Now, what we haven't discussed about SimScale is the meshing. So as you notice, I didn't worry about the meshing at all. And that's because the meshing is pretty much automated. So you can quickly build an automatic meshing. And you can, of course, add your refinement regions seamlessly. So in this case, I built a quick mesh and just refine the region around the impact where it's more important. All right. Please, if you have questions, just put them in the Q&A, and we'll try to answer all of them during the end of the session. Cool. That's how easy to set it up. Now let's go back and see some results. So here I have already simulated the model, and I can open a finished simulation and post-process the results. As the results are loading, you can see here I have saved already a couple of screenshots that can basically show me how the rim is deforming. Also showing me the plastic strains on the rim, and also showing me a quick animation of the actual impact, which you can see here, right? So that's my first design. Now you can look at the live post-processor. That's how it looks, and you can basically do all kinds of different analysis. You can basically play with the animation over here. So I can quickly just walk you through. And what I see here is maybe I can change the coloring a bit to something else. I can make it von Mises stresses, right? So I can basically see how the stresses are growing. I can bring up the legend. I can basically see the deformation at every step, and how after a few milliseconds, the anvil bounces back, and I'm left with the final shape, right? And the same I can do for all the different designs. I can also compare designs one with the other. So I can basically just compare design 2 and see the two designs side by side. So design 1 being on the left and design 2 being on the right. right? So that's also really good for marketing, right? You can basically show this to your customers as you want side by side. So you can clearly see that design one, so design two is less, is more effective, right? It performs less, right? So it might be a better candidate. All right, let me exit the mode. And let me now go back to the platform, to the slides, right? And let's start discussing the results a bit. So here I have the 3 different designs, and those are all animations I created from SimScale, right? So I have design 1, 2, and 3 side by side, seeing the animation, and I can already see from these slides that design 3 is deforming the less, right? So I can take these animations, put it in my reports, and then show it to the customers, right? Or to the, let's say, bikers, right, that are interested to buy a wheel in this case. But what I can also do is create comparative screenshots, static screenshots side by side, where I use only to plot the displacement, right? So in this case, design 1 is the initial design I had, and it's the standard width, and that deforms by 2.5 millimeters. Then I made a new variation, which is a wider profile, and that now, despite being wider, it deforms less, so that's cool, right? I managed to get a better design, but then that might also need more material after all. And then finally, I did design 3, which is slightly less wider, but it performs the best out of 3, because I think also what we did here is we made it a bit thicker, right? So we now have 3 designs to pick from based on the thickness, width, and material costs, right? And then understand which one might be more effective and more efficient for me to throw in the market, right? Now, also here, another screenshot of the same story. So what I'm plotting here is the plastic strain after impact. So the larger this region is, it means the larger the region that got permanently deformed. Apparently, design 1, it's quite big over here, you can see. Design 2 is a bit better over here on top, but it also, we can also see some plastic deformation happening here on the side, right? That's not good. And then design 3, after all, looks like to be the best out of the 3, where I get minimum deformation, plastic deformation here, but also a reduced region being deformed over here as well. So yeah, right now I'm gonna have to ask Patrick before I give it to him as well, right? We see design 3 is the best, right, in terms of performance, but is it the best one to manufacture because it might be more expensive, right?
So obviously these are slightly simplified for what we went through. These are sort of a couple of snapshots throughout the design process. And so the major goal for this product was to get the internal rim width wider. And so with that, you make the tire sit a little bit wider, and because of that, it sits a little bit flatter. So you have to increase your impact toughness. And so that's why there's the different widths. Just like a quick background for why the project's reasons as well. But so yes, so with an aluminium extrusion, there's the thinner the wall thickness is, obviously the quicker your tool will wear out. So there's some of those considerations, and then also the wider you go to maintain the same impact resistance, you're going to add weight to the product. And so we found that we went quite a lot wider, and then we came back to that design 3 where we could get a really good impact performance while adding very little weight to the final rim profile.
I get it.
So, yeah.
Great. That's really cool to know. And I guess it's not just that, right? Then you have to take these designs and then also do a CFD, right? Analysis, right? Wind tunnel.
So this is a totally different. This is a different project. So that's for cross-country mountain bike rim, and then this is some of our top-end aerodynamic road wheels. So slightly different use case, but yeah, just shows the how useful your platform is, that you can test lots of different wheels. You know.
Yeah, okay, yeah. We offer multi-physics. That's something we already communicated to everyone. So in the same project, I also have a CFD project. We could take a quick look at that in the end if we have some time. But now maybe Paddy, we can basically maybe tell us a bit more about what we're seeing here I guess you are comparing two different designs against the drag force.
Yes. So these are two different rim models that we developed entirely in SimScale, and so we went through I think it was 38 different front rim profiles to get the final selection of 3 that we took to the wind tunnel, and then these were the best 2 of the 3 we took. Both on the left here, you can see the results that we got out of SimScale using this. We did both wheel only and full bike simulations for this, and then the results that we saw in the wind tunnel. And so you can see that there's like a good correlation between the drag plots that we've got out of these two the tests. So you're seeing very similar low yaw performance between 2.19 and 2.33. And that is transferred across into the wind tunnel. And then at the higher yaws, we're seeing the 2.19 perform a little bit better, and so get a little bit of drag savings there. And so, yeah, it's like good to see that the stuff we're simulating, we're seeing it both in the real world because we're using slightly different frames. And so some of these differences could be put down to, like bike-specific phenomena, but also, to get the good correlation and to be able to rank wheels virtually is like a really important thing for us, and eventually will allow us to replace the expensive and time-consuming wind tunnel testing that we do.
Makes sense. And I guess thanks. And I guess here it's just a correlation between the different wheels and the drag, right, and the weight, right?
Yeah, exactly. So this is the new SUB50 Limitless that we've just released. Have all of the profiles were developed using SimScale, and so these are the results from the wind tunnel testing, and just showing what it enabled us to do. That we're a very small company in the grand scheme of things, and that we managed to produce a incredibly aerodynamically efficient profile that was all of the wheel sets that were shallower than us were less aerodynamic, and we were only beaten by wheel sets that were quite a lot deeper and therefore heavier than us. And so it allowed us to bring to market a really high-performing wheel set that has a really good balance between wheel set weight and aerodynamic performance. And if anyone's interested in that, we've released a full white paper on that you can find on our website.
Thank you. That's super interesting, and I'll definitely have a read of this paper afterwards. And let me, guys, just spend 1 or 2 minutes just to show you also how the CFD looks like, because we've set up an FEA, but in the same project, I have also created a virtual wind tunnel CFD, right? So you can see here, if I can hide the faces here, I have here the bike in the center, right? I created wakes, wake regions with finer meshes, and I was able to run a CFD analysis. The workflow is pretty much the same. So once you learn one tool, you can easily learn the other, doing CFD as well, right? No issues over there. And here I have 2 simulations. I have a quick run, only 4 million cells. But there I also wanted to show you that the power of SimScale and the cloud is that you can go to up to very high and large meshes, 22 million cells, 50, 60 million cells you can easily simulate, because we offer machines up to 96 cores to your availability. So in this case, I just ran the CFD study as well, and I also created images, right, where you can see and you can add your reports. Perfect. And with that, I think we can go to the last section where it's the Q&A session. So I'll hand it back to Nachman, and please, Nachman, let's spend the next, because we're a bit over time already, but let's spend the next 5 minutes maybe to answer the questions.
Great, thank you, Anis, and Paddy, thanks so much for your insights there. We do have some questions. Let's get cracking with them. And if you have any further questions, just keep posting them. And we in a follow-up email, when we send you a recording of this webinar, we might include some Q&A discussion in that email as well. So thanks so much, Paddy. It was really good to hear you talking about your R&D process and bringing bicycle tires to market. Just tell us, we have a few people asking about your workflow, your internal workflow, right? What kind of CAD tools do you use for design? How do you get your CAD models into SimScale, and at what process do you start physical prototyping, if at all, before you move to manufacturing?
So yeah, so we're fully cloud native. Yeah, that's a new phrase for me. But so we use Onshape for all of our CAD needs, and then that ports directly into SimScale. So that makes the workflow super clean, and it lets us simulate really easily and really quickly. And for physical prototypes, again, it depends on the size of the project and what we're trying to do. But for the SUB50 that we showed you, we went from CFD, and then we in-house 3D printed some prototypes that we took to the wind tunnel once, just for a final pre-production validation, and then we went and cut metal and decided on the tooling sizes. For the mountain bike wheels, it's very hard to do any accurate simulation without setting the tooling down. So for that case, we went straight from the FEA straight to final tooling, and the real world tests were good, and so we went straight from SimScale to production.
Amazing. And the wind tunnel tests you mentioned earlier, are they done on scale models? They're 3D printed scale models, or do you make them to full size?
No, we make them to full size, and we make them to full size and build them into wheels and fit them in a full size bike. And so we use the GST wind canal, which is on the Airbus site in Immenstadt in the south of Germany. So
yeah. Okay, amazing. But Johannes, we have a couple of questions on the SimScale side as well. So you showed the workflow there, where in the same project you had you had CFD, you had FEA. What other kinds of analysis, because you mentioned multiphysics, could someone do on a similar type of product where performance is very important and you need access to the cloud? So what other types of solvers are there?
So if I just go back to the platform to show you, every time I try to create a new simulation, I get all the different options. So you can basically see for yourself. We support CFD, so you can do the simplest of all, like the standard incompressible analysis. But you can also do compressible, convective heat transfer, conjugate heat transfer analysis, even multi-phase. And we also have an LBM solver that can be used for external building aerodynamics. On the structural side, we explored the dynamic analysis to do a drop impact test, right? But you can also start with a standard static structural analysis and move on to frequency, harmonic, and thermomechanical analysis, especially frequency and harmonic. We've seen them be used quite often in various different industries. Recently, we've also released electromagnetics. It's not too relevant for the specific use case we're discussing today, but it's also becoming quite important in case of like electric motors or I don't know, cables, etc.
Yeah, excellent. And Paddy, just going back to you, I know you guys you have to stay on top of performance, right? You're always innovating. That's one of your core strengths as a team and as a company, right? Because you compete in these international, your products compete in these international races where literally every second counts, right? So any edge you can extract from your products, your wheels, for example, makes a difference. What's next in terms of the R&D? I'm not telling you to spill your secrets, but what's on the horizon in terms of the use of simulation? Any cool tech coming out soon?
So I think the big thing, we've obviously, the SUB50 was a really big research project for us, and we spent about 2 years developing that product. And so we're definitely going to look to take some of our learnings and some of that high performance tech and bring that throughout some of the rest of our range. So we're going to look at transfer some of the efficiencies we've gained there and what we learned from that tech into our wider range, and so use these halo products to really develop our skills and push our product forward, but then also try and again serve all of our riders at the different price points that we sort of produce wheels at.
Brilliant. And it's good to hear that everyone who works there, they're all riders, right? So everyone understands the actual product performance metrics. Johannes, we have a user asking, an attendee asking, How do you get started with SimScale? What's a good way would you recommend for someone to jump in terms of getting started quickly? Tutorials, documentation, etc.
Really nice question. So if you're interested in commercial collaboration, you can always just mail us directly at sales@simscale.com. We'll get in touch with you and schedule a one-on-one session to understand your needs. But you can also explore SimScale via the community version we offer. So that's a free version. You can do, I think, up to 10 simulations for free. It's not meant for commercial use though, but you can easily just create a free account and start exploring. In the meantime, you can just go to our online documentation where you can find plenty of tutorials and how-to guides and test cases, right? Where you can basically just take one of them and start practicing. And then you can basically understand what are the capabilities and learn from yourself how easy it is to learn and use SimScale.
Okay, excellent. I think that's a good time to wrap it up. Thanks so much from my side to everyone attending. Like I mentioned earlier, we will share a recording of this live webinar with everyone. Give us a couple of days just to process the video, and we'll share that by email. Thanks so much to our guest presenter, Paddy from Hunt, and Oanis. Oanis, I'll hand over to you for some closing remarks. Thank you.
Thank you, Nachman. Thank you, Paddy. It was a pleasure working with you to prepare this webinar. Thank you for joining us, and thank you everyone for attending. Feel free, you have our contact details here. Both me and Paddy are really happy to answer any questions related to this webinar, but also related to simulation and I guess hand bike wheel products in general. So feel free just to send us an email if you have any further questions. And happy I've been here. Take a look at our webinars page to follow the upcoming webinars or even the past ones to see if you can find anything else which is interesting for you. Thank you guys and have a nice rest of the day.